In this section, we are going to learn about the calculus of vector-valued functions, specifically differentiation and integration. So let's assume we have some vector-valued function that takes in our single variable parameter and spits out a vector. Okay, and for simplicity, let's assume we're dealing with R2. The same argument holds for R3 or any number of dimensions. But so we don't have to write too much. Let's stick with R2. Okay. So what do we mean when we take the derivative of a vector-valued function? So the definition here will be familiar. It's the same difference quotient definition that we're used to. It just involves vectors now instead of scalar functions. Okay, so we want to take the limit as h goes to 0 of r of t plus h minus r of t all over h. Okay, same formula we've been working with. What does it look like, though, when I plug in the components for my vector-valued function? Okay, so here we're going to assume r of t has two components, where the first component is x of t, and the second component is y of t. Okay, so for this first guy, I have r of t plus h, so I just swap out all my t's with t plus h. So the r of t plus h is equal to the vector, where the first component is x of t plus h, and the second component is y of t plus h. And then r of t, that's exactly what we have written here. We'll just write it again. R of t is the vector-valued function, where the first component is x of t, and the second component is y of t. And it's all over h. Okay? Now let's do a little vector arithmetic. In the numerator of this fraction, we have some vector subtraction. And so if I do the vector subtraction, I get first component minus first component. So that's x of t plus h minus x of t, comma, and then second component minus second component, y of t plus h minus y of t. All divided by h. Okay, how do I divide a vector by h? Remember, we really think about that as scalar multiplication. So we could think about this as 1 over h times the vector-valued function, x of t plus h minus x of t, comma, y of t plus h minus y of t. So multiply that 1 over h through. My first component becomes x of t plus h minus x of t all over h, comma, y of t plus h minus y of t all over h. Okay, we're almost done. There's one other thing we could do. Remember, the limit of a vector-valued function only exists if the limit of each of its components exists. So I can move this limit in, and instead of taking the limit of the vector-valued function as a whole, I could take the limit of each component. So limit as h approaches 0 of x of t plus h minus x of t over h. And the second component, move that limit in. I get limit as h approaches 0 of y of t plus h minus y of t over h. Okay, now these two look familiar. What do these look like? Those are the definition of the derivative, and not even the definition of a derivative of a vector-valued function. X of t and y of t, those are scalar functions. I'm taking in a t and I'm spitting out one value, right? Either the x value or the y value. So when I put it in a form like this, this is just a traditional calculus 1 derivative. And so I end up with the derivative of the first component and the derivative of the second component. Which means taking the derivative of a vector valued function is really easy. Assuming the derivative exists, let's write it as a theorem. Assuming the derivative exists, the derivative of a vector valued function will just be the derivative of its component functions. So again, I will a vector valued function R of t is differentiable if and only if its component functions are differentiable. In two dimensions, if R of t equals x of t, y of t, then R prime of t, to find the derivative of the vector valued function, you just take the derivatives of the individual component functions, provided the derivatives exist, right? If either one of these derivatives does not exist, then the derivative of the entire vector valued function does not exist, okay? Similarly, in R3, if R of t equals x of t, y of t, z of t, then the derivative of the vector valued function is just the new function where the components are the derivatives of the components of R of t. We just take the derivatives of each component. Let's take a look at an example. We have a vector valued function R of t. We want to find the derivative R prime of t. Okay, so we know that we just need to take the derivative of each component. So let's start with x of t. We know x of t is equal to -4 tangent of 5t squared plus 1. Okay, so let's find x prime of t. So first off, -4 is a constant in front. It comes along for the ride. Derivative of tangent is secant squared. Okay, make sure you keep the inside the same. We do need a chain rule here because it's not just tangent of t, right? It's tangent of something else. Whenever that happens, we need a chain rule. Okay, so now I'm going to multiply by the derivative of the inside. Derivative of 5t squared plus 1 is 10t. And that's my derivative of the first component. Okay, just tidy it up a little bit. -4 times the 10 is -40 times this t, secant squared 5t squared plus 1. Okay, first component done. Look at the next component. Y of t equals 2t over 3t squared plus 4. Now that is a quotient, so we're going to need the quotient rule. Okay, so that's derivative of the top times the bottom unchanged minus the top unchanged times the derivative of the bottom divided by the bottom squared. Okay, let's see if we could tidy that up just a bit. Okay, so I'm going to distribute the 2. I'm going to multiply the 2t and the 6t over here. Okay, I end up getting 6t squared plus 8 from this. And then here I get minus 12t squared. And I'm going to leave this as it is. Generally, things that are factored are more useful than things that are not factored. So you have to have a good reason to unfactor something. I'm going to leave this as 3t squared plus 4 squared. Okay? And then in the numerator, I can combine my like terms. I get 8 minus 6t squared over 3t squared plus 4 squared. Okay? And if I want to, I can factor out, I'll factor out a negative 2. Leaves me with 3t squared minus 4 over 3t squared plus 4 squared. Okay, and that's as good as it's going to get. I wanted to factor out this too, especially to show you that you cannot cancel these. 3t squared minus 4 and 3t squared plus 4, they look so tempting to just cancel them. They're almost the same, right? But you can't. They're not the same. One has a plus in the middle, one has a minus in the middle, and there's nothing we can do about it. Okay, so that is as good as it gets. All right, we've done 2 of our components, 1 more component to go. So we've done x of t and we've done y of t. Now let's do the third component, z of t. Okay, give myself a little horizontal room here. So z of t is equal to e to the cosine t plus natural log of t minus 3. Okay, so let's take the derivative. Let's find z prime of t. Notice for both of these, I can handle these separately first off because they're separated by a plus. Okay. For e to the cosine t and for natural log of t minus 3, I'm going to need a chain rule, right? Because this isn't just e to the t. This isn't just natural log of t. And because we have that extra complexity, we need the chain rule. So let's start with e to the cosine t. The derivative of e to something is e to something, right? It's just its own derivative. But then I need the chain rule because the something up here isn't just t. So derivative of that something, derivative of the cosine of t is negative sine of t. And the first term is done. Now let's add the derivative of natural log of t minus 3. Okay, same thing. We first take the derivative of natural log of the something. Derivative of natural log of something is 1 over the something. So 1 over t minus 3. But because this something isn't just t, I need to multiply by the derivative of the something, by the chain rule. Okay, derivative of t minus 3 is just 1. And so put it all together, tidy it up just a bit, I get negative sine of t times e to the cosine of t plus 1 over t minus 3. That's about as good as it gets. All right, so now let's put it all together for our final answer. The derivative of the vector valued function is the vector valued function where the components are the derivative of the components of the original function. So x prime of t, y prime of t, z prime of t, we found those. X prime of t was negative 40t secant squared 5t squared plus 1. Negative 40t secant squared 5t squared plus 1. Double check I got that right. Yeah. Y prime of t was negative 2 3t squared minus 4 over 3t squared plus 4 squared. Negative 2 3t squared minus 4 over 3t squared plus 4 squared. And finally, my third component, z prime of t, is negative sine t e to the cosine t plus 1 over t minus 3. negative sine of t e to the cosine of t plus 1 over t minus 3. Okay, if you want to be very careful about what's inside the sign and what's not, you could put parentheses around the t's here and here. Okay, that's my answer. That is the derivative of my vector valued function. Okay, great. We know how to take the derivative of a vector valued function, but what does it mean? How do we interpret the derivative of a vector valued function? We know with scalar functions, with one variable functions, the derivative gives us the slope of the tangent line. Do we have a similar kind of explanation for the derivative for vector valued functions? Okay, so let's take a look at the definition to understand what's going on here. Okay. The derivative of a vector valued function, by definition, is the limit as h approaches 0 of r of t plus h minus r of t over h. Now we can get some intuition on what this derivative is doing by kind of thinking of this pictorially. So imagine this curve is the graph of r of t. Okay? And let's focus on the derivative at a particular point. Instead of thinking about the derivative function, let's think about the derivative at one point where t is equal to some value. Say it's equal to a. Okay, maybe a is 7, maybe it's negative 4, but we're looking at a particular value on the curve. Okay? So let's assume this is the point where t is equal to a. That's the point that we get out of the vector valued function when t equals a. Okay? Now what we want is we want this vector subtraction. Let's focus on just the numerator for now. And let's think about this vector subtraction. So this gives me that point there, right? And then I add some h to it. And I look further down the curve, maybe over here. Okay? Maybe this is r of a plus h. Okay? That's the point there. Now, of course, h is going to change. We're going to let h get smaller and smaller. As h gets smaller, this point will move back along the curve. Right? But for now, what do we get with this? Well, when we take this and subtract that, we'll get a vector. We're doing vector subtraction here. And so the resultant vector is n minus start. It's the vector that will end at this point and starts at that point. Okay? This is the vector r of a plus h minus r of a. Okay? Now, what we want to do is we want to think about what happens to this vector. What happened, which is the numerator of this fraction. What happens to this as we let h approach 0? Okay? If h is approaching 0, that means this point is going to go back along this path, getting closer and closer to the original point r of a. Okay? So what happens is we let those 2 points get close together. Maybe I should use a different color here to emphasize it's a different point. Okay? I just want to make it clear that this is the point we're moving and not this one. So let's start moving it back. Let's make h a little closer to 0. We get this point, okay? So now that numerator is this vector here, right? N minus start. Okay, let's move the point a little further down this track. Okay, let's go to here. Okay, now if I do the vector subtraction, I get this vector. keep on going. What am I getting closer to here? The closer I get, the closer h gets to 0, the closer this point gets to this point. And the more that this vector that points from one to the other, the closer it gets to being a vector tangent to the curve. Okay? And so that's what this is getting us. It's getting us closer and closer to some vector that is tangent to the curve right here. Okay, let me use a different color, see if that'll show up a little better. Okay, that's what we're looking for, a vector tangent to the curve. What does that say about h then? We've talked about the numerator. What's the denominator here doing? The denominator is kind of normalizing things. Okay, for big H, we expect the vector here to be kind of big. But as h gets closer and closer to 0, what's happening to the vector? It's getting smaller and smaller and smaller, right? By dividing by h, it kind of corrects for that length adjustment. Otherwise, by the time we get back here, the length of the vector would be 0, right? So the derivative of r of t at the point t equals a gives a vector tangent to the curve r of t at the point t equals a. Okay? So that's what the derivative is doing. It's giving us a tangent vector. All right? The length of the vector is also significant, though we're not going to focus much on it in this section. We'll focus more on it in future sections. But if you remember that we could think about our parameter as time. And so what the original function is telling us is you could almost imagine a particle moving along this path at different points in time, right? And maybe sometimes it's moving faster and sometimes it's moving slower. The length of the derivative tells us how fast we're moving. A longer vector tells us we're moving faster. A shorter vector tells us we're moving slower. Taken together, the derivative tells us both direction and speed that a particle is moving along the curve with that parameterization. Okay, it's giving us the velocity. If r of t is a position function, then r prime is the velocity function. Let's use our newfound knowledge of how to interpret the derivative to take a look at some examples. Okay, here we have a vector valued function. We want to find a line tangent to that vector valued function when t is equal to 1. Okay. So first off, notice that it says line. We know the derivative of a vector valued function gives a vector tangent to the curve at any particular point in time. We don't want just a vector tangent to the curve. We want the line tangent to the curve, right? So we have some vector valued function, okay? It has an orientation to it. This is our r of t, for say, okay? And there's a point here somewhere. Let me color it blue. this is the point that we get when t is 1. So maybe this is r of 1. What we want is a line tangent. We want a line tangent to the curve at that point. Okay? We know how to find the equation of a line, right? The equation of a line is equal to some point on the line plus t times a direction vector. That points parallel to the line. Okay? Okay, so we need both of these things to find the equation of the line. Okay, let's start with point on the line. That's going to be easy, right? Because it's just going to be this point. R of t, for any value of t, it tells us the point at that value of t. Okay, we're interested in particular at the point when t equals 1. So the point on the line that we can use here is just going to be r of 1. So I'm going to get, if I plug in 1, I get, what, -6 for the first component. Plug in 1 to the second component, I get -2e. And plug in 1 for the second component, I get -4e to the -1. Okay? I mean, not the prettiest vector in the world, but that's what it is. That is a point that I know is on the line because that's where the line hits. That's where the line intersects the curve. Okay, that's where we want to be tangent at. If we're going to be tangent at the point, it's actually got to hit the point. Okay, so this one's down. We got it. Now we need a direction vector. Okay, this is where that other piece of information comes in. If we had a vector tangent to the line, then that vector would be a direction vector that we could use. Okay, we could find a vector tangent to the line. That's just the derivative, right? The derivative tells us a vector that is tangent to the curve. So if I can find the derivative, so for our direction vector, we're going to start by finding the derivative. And I just take the derivative of each component. So derivative of the first component, -5t minus 1, it's just -5. Derivative of the second component is -2e to the t. And the derivative of the third component, it's -4e to the -t. So if I take the derivative of that, I get -4 comes along for the ride. Derivative of e to the -t is e to the -t times the derivative of this, because I need the chain rule here, since it's not just e to the t, it's e to the -t. So I need to multiply by the derivative of the thing that's not t that I'm plugging in, that I normally would think of as t. Okay, so -5, -2e to the t, and then -4 times the -1 gives me +4e to the -t. Okay, that's my derivative. Now, I don't want that whole derivative. I only care about the direction vector at this particular point, when t is equal to 1. So I need to plug in 1 into my derivative function. I need to plug t equals 1 into my derivative function so I could get the tangent vector at t equals 1. So if I plug in 1, I get -5, -2e to the 1, and 4e to the -1. So that's my direction vector when t equals 1. That is a point that the tangent line will pass through. It's the point that the line is tangent at. Right? So put it together, I get my tangent line. My tangent line, L of t, is going to be a point on the line, -6, -2e, -4e to the -1, plus t times a vector parallel to the line, a direction vector. And we found that the vector tangent to the curve when t is equal to 1 is going to be this vector here. So that's also a vector that's pointing in the direction of the line. That's our direction vector. And so there, put it all together, we get our tangent vector at the point t equals 1. Let's take a look at another example. Here we have two curves. We know they intersect at a point. We want to find the angle of intersection. Okay, so let's draw a very rough picture. This is not going to be especially exact at all. Okay, but f of x equals x squared minus x minus 2, that's a parabola, and it opens up. Okay, so maybe this is f of x, and then g of x, 4x minus 8, that's a line with slope 4. So maybe it intersects, maybe it goes through like this. Okay, and it intersects at some point here, 2, 0. Okay, now of course it intersects at another point, but they're asking us specifically at 2, 0. Or maybe these particular two graphs only do intersect at one point. We don't know for sure, okay, unless you want to actually go and graph it. It's not really relevant to the problem though, okay? We want to know the acute angle of intersection. That is, if we kind of take the tangent vector here and the tangent vector here, what's the angle that we get? Okay, that's what we want. And notice we have to be careful because there are multiple possible answers here. There's that one that I showed, but I could also maybe get this one here. Okay, that angle. In this case, we want the acute angle of intersection. That means it should be smaller than 90 degrees. All right, so it should be the smaller angle. If I do the math and I get an angle bigger than 90 degrees, I could just subtract it from 180 and get the smaller angle. Okay, so in order to do this, let's go back to this one because this is the angle we actually want. Okay, in order to get something like this, we need vectors, right? Vectors would be fantastic here because if we had tangent vectors, they'd be pointing exactly where we need to go, and we have tools to find the angles between vectors, such as the dot product, right? These functions, though, they're not vector valued functions. These are single variable calculus 1 level functions. The tools that we have that are going to be easiest to work with here are tools that work for vector valued functions, that work for vectors. So before we jump in, let's parameterize these curves. Let's find vector valued functions that trace out these curves. Okay? So for f of x equals x squared minus x minus 2, I'm going to do the absolute easiest thing to find a parameterization for these curves. I'm going to let x be t. Then the y value, if x is t, the y value would just be t squared minus t minus 2. See how that works? Do the same thing for g. G of x equals 4x minus 8. Let's see, let's call this R1, so we'll call this R2. And I don't want us to confuse this t with this parameter, so I'm going to give this parameter a different name. I'm going to call it s. Okay? I'm going to do the exact same thing, though. I'm going to let x be s, and that means the y value, the output value of this function, would be 4x minus 8. If I plug in s for x, that's 4s minus 8. And so now I have two vector valued functions that parameterize these two curves, that trace out these two curves. Okay? They intersect at the point 2, 0. Now, the t value when this guy reaches 2 comma 0 may not always be the same parameter that this guy reaches 2 comma 0 at. Okay. So we need to figure out what is the value of t when this function reaches this point, and what is the value of s when this function reaches this point. We're going to need that in order to find at exactly what t and exactly what s do we have our do we want to calculate our tangent vectors at. Okay. So I'm going to set this equal to 2, 0. And this is real easy to calculate. The only way this is going to work is if this component and this component are equal, so t has to be 2. Okay, and if you want to test that it works here, 2 squared is 4, minus 2 again, it is 0. Okay, so this function hits the point 2, 0, the point of intersection, when t is 2. Okay, let's take a look at this one. Now let's find out when this one hits 2, 0. Oh, hey, how about that? This one hits 2, 0 when s is 2, since this and this have to be equal. Okay. Now, in this particular case, these are the same value. Just be aware that they don't always have to be the same value. Okay. But now we know that this function, this vector valued function, hits the point of intersection when t is 2. This vector valued function reaches the point of intersection when s is 2. Okay? So now that we know when we hit the point of intersection, we need tangent vectors at the point of intersection. Once we have those tangent vectors, okay, we can use the dot product to find the angle between them. That's the plan. Okay? So to find the tangent vectors, I need the derivative of each of these vector values functions. So let's take the derivative of the first vector valued function here. I get 1 comma 2t minus 1. Just taking the derivative of each component individually. And let's do it for the second function here. R2 prime of s, I get 1 comma 4. Okay? And I'm interested in the tangent vector at a particular value of t, at a particular value of s. So let's plug that in. So at t equals 2, I get 1 comma 3. That's the tangent vector of this first function when the two functions intersect. Okay? And if I plug in 2 here, there's really not a whole lot to do in this case because the vector is just constant. It just stays 1 comma 4. Okay? These are our two tangent vectors. Two tangent vectors. Now let's find the angle between them. So I know that the dot product of these two vectors, here, let's do it this way. The dot product of the tangent vector tangent to the first function with the vector tangent at the point of intersection to the second function is going to be the norm of the first vector times the norm of the second vector times cosine of the angle between them. Okay? Dot product, I just get 1 times 1 plus 3 times 4. I get 1 plus 12. And then over here, let's take those norms. I have 1 squared plus 3 squared for my first norm. I have 1 squared plus 4 squared for my second norm. Cosine theta. So I get 13 equals square root of 10 times the square root of 17. So divide by root 10, divide by root 17. I get 13 over root 170, if you want to multiply them, equals cosine theta, which means theta is going to be the arc cosine of 13 over root 170. Whew, okay, we're almost done. We just need to plug that thing into a calculator now. Pulling the calculator over. We're in degrees. We want to be in degrees. The instructions asked us for the acute angle in degrees. So let's find the arc cosine of 13 over the square root of 170 in degrees. Okay, and we get 4.3987 degrees. That is an acute angle. Remember, we want an acute angle, an angle less than 90. That is acute, which means we're done. That was 4.3987. Okay. If it wasn't the acute angle, then it would have been the larger angle. And the acute angle plus the larger angle equals 180. So I could have found the acute angle by subtracting the angle I did find from 180. Okay, so if you do get an angle larger than 90 degrees with a problem like this, you can find the acute angle by taking the angle you get and subtracting it from 180 degrees. In this example, we're going to introduce a new concept, though it is a straightforward concept. We want to find the unit tangent vector to the curve at t equals 2. A lot of times when we're dealing with these parameterized curves, we're more focused on the direction of the tangent line than or the tangent vector than the length of the tangent vector. Remember, the length kind of communicates the speed with which a particle would move along the trajectory, okay? Based on if t is time, okay? But sometimes we just care about the shape of the tangent curve, not how fast the particle would move along it. When we want to focus on just the shape of the tangent curve, we only care about the direction a tangent vector is pointing, not the length of the tangent vector. When we want to emphasize the direction of a tangent vector, we turn it into a unit vector, the unit tangent vector, okay? The unit tangent vector, we usually use capital T. At a point T is just the tangent vector, which is the derivative at point T, and then we normalize it to turn it into a unit vector, allowing us to focus on just the direction without worrying about the magnitude. Okay, so we're just going to find r prime of t, which in this case is 3, 5, and then here 9 minus t squared under a root. It's 9 minus t squared to the half, remember. So we need a power rule and a chain rule. So I'm going to apply the power rule to the outside first. So bring down the power, subtract 1 from the power, and then multiply by the derivative on the inside based on the chain rule. Derivative of 9 minus t squared is negative 2t. Okay? And just tidy that up. 3, 5, and then the 2's cancel. The negative 1/2, the negative moves that term, that factor to the denominator. The half makes it a root. So 9 minus t squared under a root in the denominator, and then I still have this negative t on top. Okay, so there's my derivative. I don't care about the derivative at all points, though. I'm only interested in what's happening at t equals 2. So plug in t equals 2. I get 3, 5, and negative 2 over root 9 minus 2 squared is 4. So that's 3, 5, negative 2 over square root of 5. Okay, that's my r prime of 2. In order to find my unit tangent vector, I now want to normalize this. Okay, so the unit tangent vector when t is 2 is a tangent vector when t is 2 divided by the length of that vector. So I normalize it, turn it into a unit vector. Okay, we know the vector on top, we just calculated it. 3, 5, negative 2 over root 5. On bottom, we need to find the norm of r prime of 2. So the norm of this. So square root of first component squared plus second component squared plus third component squared. So my numerator stays the same. In the denominator, I have 9 plus 25, that's 34. And then here, if I square this, negative squared becomes positive. 2 squared is 4, and square root of 5 squared is 5. So I get plus 4/5. We're going to need a common denominator for this. 34 times 5 is what, 170 over 5. So 34 is 170 over 5. That gets us a common denominator. Now I could add them together. And I get, give myself a little more room here. 3, 5, negative 2 over root 5 over square root of 170 over 5. I'm dividing by a fraction. Fraction under square root, but it's still a fraction. When I'm dividing by a fraction, I can multiply by the reciprocal. And so this becomes square root of 5 over 170 times the vector 3, 5, negative 2 over root 5. And now I'm going to scalar multiply it through. I get 3 root 5 over 170. I get 5 times root 5 over 170. And when I multiply it by this, the root 5 on bottom and the root 5 on top will cancel. So I'll just have negative 2 on top and root 170 on bottom. That is the unit tangent vector at t equals 2. Let's finish off this section with a discussion of integration. So based on what we've learned about derivatives, it should not be surprising that if we want to integrate a vector valued function, we just integrate each of the component functions. Okay, so the integral of the vector valued function r of t with respect to t, I would just separately integrate each component function. So x of t, I'd integrate y of t, and I'd integrate z of t if there is that third component. Okay? So pretty straightforward. I'm more interested in the interpretation. Okay? We know to think about integration as kind of a lot of addition, right? This infinite addition of these infinitely small terms. So let's look at this discretely. If we're adding up a bunch of vectors, how do we think of vector addition? We usually draw the vector's tail to tip, right? And the resulting vector gives us the vector from the start to the tip of the last vector, right? So thinking about this as an indefinite integral, the idea is you start at some point, okay, and you add in that first vector. And then you add in that second vector. And then maybe you add in the third vector. And the fourth vector, okay? With integration, you're just adding all these vectors together. So if we sketch them tail to tip, with each vector, we're kind of tracing out a curve, aren't we? So it undoes what we do with derivatives. Just like in the single variable case. Single variable case, if we take the indefinite integral of a derivative, we get back the original function, plus or minus a constant, right? Same thing with vector valued functions. If you imagine adding up all these little tangent vectors, the tangent vector tells us what direction we're in, and if we kind of put them all together, we end up getting the curve back. Okay, so that's how to think about this vector integration. All right, so let's do some examples. So first example, this is going to be a definite integral. We want to integrate the vector valued function 1 over ti plus t squared j. We're going to integrate it from 1 to e, so it's a definite integral. Okay, so 1 over e, 1 over ti plus t squared j dt. And we're going to integrate each component individually. So I'm going to first worry about the 1 over t. And then I worry about the other component, t squared. I'm going to integrate them both. Okay. Integral of 1 over t is easy, if you remember it. You do have to be a little careful with 1 over t. This is t to the negative 1, right? So you might think, oh, we do a power rule. But remember, this is the one case where the power rule fails. The antiderivative of 1 over t is natural log of the absolute value of t. Okay? And we're going to evaluate that from 1 to e. Same thing here. This one we will use the power rule. We got t squared. So I'm going to add 1 to the power, divide by my new power, and I'm going to evaluate that from 1 to e. Okay? The antiderivative part of this is done. Now all I have to do is plug in the limits of integration. In this case, 1 and e are both positive, so when I plug them in, I can drop the absolute value, right? So I'm going to get natural log of e minus natural log of 1. That's my first component of my vector. Of my vector. And here, plug in the e, I get e cubed over 3. Plug in the 1, I get 1 cubed over 3. That's my second component, my j component. Okay? Now over here, if you know your natural logs well, you know we could simplify these. Natural log of e is just 1, right? Remember, natural log is just the opposite of an exponential function. So if, say, y equals natural log of e, that also means e to the means e to the 1 equals e, because this is log base e, right? So e to the, I'm sorry, not e to the 1, e to the y. E to the y equals e. So this is base e, okay? So base e to the y equals e. Okay, which means we could see y as 1. This exponent and this exponent have to be equal, and this exponent is an invisible 1. So natural log of e is 1. We do the same thing with natural log of 1. I'll do it in a different color. Y equals natural log of 1. This natural log is base e, so that means e to the y equals 1. Okay, so e to what power equals 1? Well, e to the 0 equals 1. Right, so natural log of 1 is 0. and natural log of e is 1. Okay, over on this side, there's thus I can do on this side. 1 cubed is just 1, and I do have a common denominator. So if I combine the two fractions into a single fraction, I get e cubed minus 1 over 3. And so my final answer, 1 minus 0 is just 1, so I get 1i plus e cubed minus 1 over 3j. Okay, so that's a definite integral. Let's see what it looks like with an indefinite integral. Now, this one's going to be a little trickier. Just the functions are a little rougher. Okay, but the idea is the same. We want the antiderivative, the indefinite integral of our vector valued function r of t. And to do that, we're going to take the indefinite integral of each component function. So I'm going to take the integral of my first function, negative 5t to the 5th plus 4. Okay, I'm going to take an integral of my second function, negative 5e to the negative t. And integrate my last function, 2 sine negative 4t. Okay, the first one's pretty straightforward. I just have two terms. For the first term, I use the power rule, right? Add 1 to the power, divide by the new power. The negative 5 in front just comes along for the ride. It's just a constant. Okay, and the 4 is just a constant all by itself. Integral of a constant all by itself is just the constant times the variable. So 4t. Okay, this is an indefinite integral, so I will get a plus c, right? Now I'm going to be very careful. I'm going to say plus cx here. Okay, this is my c, my constant from my first component, from my x component. Okay, let's do this one now. Negative 5e to the negative t. If you know your integrals real well, you'll know the negative 5 comes along for the ride. The integral of e to the negative t is e to the negative t, but then I have to divide by negative 1. So I end up getting 5e to the negative t. Okay, the negative 5 here cancels with the negative here. Now, you can always use substitution here, right? So I could let u equal negative t. Du dt would be negative 1, so that's where that extra negative 1 comes from. So du equals negative dt. Okay, so writing it like that, I get negative 5 times the negative becomes positive 5. E to the negative t becomes e to the u, since negative t is u. And dt, well, negative dt becomes du, but I've already dealt with the negative, right? Integral of e to the u is e to the u, but u is negative t. So that's where I get e to the negative t with 5 in front. Okay. One more. Oh, I forgot something though, right? It's an indefinite integral. I need a constant. Okay. This constant doesn't have to be the same as that constant. They could be two completely different constants because they're part of two different integrals at the component level, right? And then let's do this one. The 2 comes along for the ride. And again, if you're real familiar with integrals, you have a linear term like this. I'm just going to end up dividing by a negative 4. Okay, so 2 over negative 4. And then the integral of sine is negative cosine. Okay, so that was probably too fast for some of you. Let's also look at it using substitution. So using substitution, I would let u be negative 4t. If I take the derivative of both sides with respect to t, du dt is negative 4. Okay, so if I divide by negative 4, get the dt by itself, then I could swap out the dt with du over negative 4. That's why I'm dividing by the negative 4. Okay, so I'll pull the 2 out. Integral of sine negative 4t becomes my u, and dt becomes du over negative 4. Du over negative 4. Okay, so that's where I get the 2 over negative 4. And then integral of sine is negative cosine. And then the u is negative 4t. Plus a constant, right? So essentially I'm done. Though in each term I have a constant. Let's break this up into pieces. So I'm going to break this up into a vector without constants. So negative 5t to the 6 over 6 plus 4t. And I'll leave off the cx for now. 5e to the negative t. I'll leave off the cy for now. And then here, I'm going to simplify this. That's positive 1 over 2 once it's simplified. Cosine of negative 4t. And then I leave the cz off for now. But I'll put all those constants in a separate vector over here. Okay, so each term gets its constant. And so I can call this vector of constants just a constant vector. So instead of having each component added a c, it's easier to just at the end add one big vector of constants. So this stays the same. 5t6 over 6 plus 4t, comma 5e to the negative t, comma 1 over 2 cosine of negative 4t, plus a vector of constants. And that is the indefinite integral of the vector valued function.